This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
Good afternoon, everyone, and welcome to EE380, the Computer Systems Colloquium in the Electrical Engineering Department at Stanford. Today's speaker, as everyone seems to know because the room is packed, is Dave Patterson from Berkeley. I'll just give a quick introduction because he probably doesn't need one, but just to get us on the same page. Dave Patterson has a bachelor's degree in math and a master's and PhD in computer science from UCLA. He's been a professor at Berkeley in computer science since 1977. He is a pioneer of RISC and also of RAID. He's done a lot of work in computer architecture, and most of you have probably read one or more of his various books. How many people here took their undergrad architecture classes with one of his books? That's great. For those of you watching online, it's about a third of the room, and there's well over 100 people here. So. It's very interesting. All right, he's going to talk to you today about Berkeley's view on multiprocessing and parallel processing. Please welcome Dave Patterson.
Thanks. It's great to be back here with our friendly rivals across the bay. So this is a really exciting. I can't, it's hard for somehow a guy who's only in his 30s, has been at Berkeley 30 years. So now. I'm in my 30s hexadecimal, so that's probably. So what's going? This is an amazing time, right? This is an amazing time. Everything is changing. Everything that we know, and I'll go over that. And we desperately need this new approach. And so I was trying to think of what the analogy is. Of course, those people know about sports. So in football, there's this thing called a Hail Mary, and what that is if you know religion, Hail Mary is the Catholic thing, when you need something, you need your prayer answered, right? So industry has basically thrown a Hail Mary. We're betting our company on parallel computing. Now the way the Hail Marys work, there's one part's throwing it, but the big part is catching it, right? So they've thrown the Hail, it's tossed. It's going to double the number of processors from now on, and this, reinvent the programming model that we're going to have to teach undergraduate students differently as a result of this Hail Mary. And they're just counting on us to race down into the end zone, figure out how to catch this ball. So this is a pretty exciting time. For researchers, this is great. You're going to come to companies, here's my crazy idea, and they're going to have to listen to you, right? Whereas before the Hail Mary, they'd say parallelism, there's no market in that, people have failed the whole time. So this is a really exciting time. So that's basically the intro to what I'm talking about. So I'll go over these, what's happened over over the last 10 or 15 years of old versus new conventional wisdom of what a big change. The questions that we came up with this study group, how should we do benchmarks in this brave new world? What do we think, what's our bet of the building blocks? What do we think programming should be? How are we going to do this? Can we do other things than compilers? What should operating systems look like? How can we do innovative computer architecture without custom chips, and how can we be successful? So there's a dozen of these. So it was always striking to me that when you were doing microprocessor design, you could just keep increasing the power and nobody said anything, right? You just increase the power and it's okay. So the idea was, you get a transistor budget, as much performance as you want, and you can use as much power as you want. It's more or less for 20 years that way. But now we're at the power war, where it's power that's expensive and transistors are free. They're not really free, but you can design more transistors today than you can turn on. Only concern was dynamic power, that if it's just sitting there, it's not using power, right? Well, the static power is now typically often 40%. 40% of the power is just when it's sitting there not doing anything. Microprocessors were extraordinarily reliable, which was a way computers got more reliable when there were fewer chips in the system because it was the pins that were the problem. That's old conventional wisdom. New conventional wisdom, as we get things much smaller feature sizes, not only will we have much higher soft error rates than we ever used to have, it's actually going to wear out and break. We're going to have hard error rates. This is something that computer designers didn't have to worry about in the past. What's a reason, like I say, computer architecture is back for about the last 15 years or so. We've just been taking Moore's law with more transistors and figuring out some way to sustain the sequential programming model, just wasting transistors hither and yon. And so the designs got bigger and bigger. And CAD tools and abstraction will let us do that. Now there's a whole bunch of physical effects that makes that really hard to do. As we get things really small, it's either going to take a lot more time or a lot more money to keep building these giant designs. In the good old days, people at Stanford and Berkeley could build chips that were genuinely faster than what Intel could build. We could build them and you could run programs and we could run them faster, which was an amazing thing. How could that be true? That can't happen anymore. There's no way that can happen. The cost of the mass, the cost of the CAD software, and gigahertz clock rates really takes a lot of time. So we can't build believable chips if we have this great idea. You know, performance, if you didn't pay attention, you might think performance improved latency and bandwidth. It's actually the bandwidth that goes up a lot more than the latency. Now, here's the killer things, right? When I took classes in programming, if I wanted to run faster, I'd get rid of multiplies, and the loads and stores are fast, right? Today, there's the memory wall. Loads are slower, but multiplies are fast. So 200 clock cycles to access a DRAM memory, but maybe if multiplies 4 clock cycles. That's like a floating point multiplier. So you may not make your program run faster, replace a load by 4 floating point multiplies. That's the world we're in today. And we've been betting on instruction level parallelism that architecture innovation and compilers reveal, and that's what's been happening for the last 15 years or so. And there are people who said 10 years ago, don't worry, that's going to keep going. We'll be able, and that was actually one of the bets of the Athenaeum. Why did they change the instruction set? There was going to be so much parallelism that VLIW was going to unveil that we'll be able to keep going. And we are at an ILP wall today. Nobody believes that that's going to work anymore. So the old convention of wisdom, what newspaper reporters thought was Moore's law, not twice as many transistors, was that you double performance every 18 months, is, you know, power wall plus memory wall equals brick wall, right? So the good thing about, by the way, there was somebody else involved in my books. I can't remember what his name was. It's Patterson. Oh yeah. Hennessy, that's who it was. Hennessy was the other guy. So the good, we've on our 4th edition, and kind of the historical thing when you're around 30 years and you've done 4 editions, you can look back through the editions and connect things together. So this is spec int translated across spec generations, going back to the early days. Back when John and I joined Stanford and Berkeley, in this era, the VAX 11780 was announced. And as I look back historically, we just thought that was the greatest thing ever, a 32-bit mini computer. This was great stuff. It didn't get any faster for 6 years. There was no faster successor for 6 years. And we just thought it was great. Wow, what a world. And then they finally got it 50% faster. And then a few years after that, they actually got it 5 times faster. But then the RISC stuff took in. And we were, I think we'll look back historically, is this renaissance in processor performance where it doubled. It really did double for integer programs every 18 months for 15, 16 years. But if you haven't been paying attention, that stopped in 2002 or 2003, and since then it's fallen off. If it had continued through last year, processors running spec int would be about 3 times faster than what you can buy today. So that's the brick wall.
So Dave, a quick question. So the first 84 dot is 785, and the second one is 8800.
Yeah, I think that's right. I think this is the 785,
Right, the cache.
and this is the
600.
I think that's right. Yeah. This doesn't make these. See, if you're old, numbers like this you get really excited. The 1600. You flash back to that. Yeah, but if you remember what spec was quoted in terms of VAX. VAX was the reference point. So. Okay, so this has led to this Hail Mary, where a sea change in chip design, where multiple processors, or it's called multiple cores per chip, is how they're going to get performance in the future. So again, the historical perspective, that's the good old 4004, which was just 35 years ago. 2,312 transistors in that technology. You could almost see every transistor there. RISC-2, one of my favorite microprocessors, well, in a modern technology and a not so big chip, you could have exactly 2,312 RISC processors in that space with some amount of cache and memory and bandwidth. And there's, I/O things, but there's a lot of innovation in packaging to overcome that. So the processor is the new transistor. That's kind of the startling for those of us who remember these old numbers. It's not the transistor you're designing, it's the processor. Why? That's what the opportunity for us. We could build things with thousands of processors. People are building things today with hundreds of processors. So in the past, it was the increasing clock frequency. Now it's parallelism is how you're going to get performance improvement. In the past, don't waste your time parallelizing an app for this parallel computer. You just wait for the next faster sequential computer, and that's not coming. Nobody's making that anymore. And that's what a statement. This is the end of the sequential microprocessor era. That's over. No one, Intel, IBM, Sun, AMD, no one's building sequential microprocessors anymore. So I think of it as the end of the lazy boy era of programming. So lazy boy is a lounge chair, you just sit there. So I'm going to write my code parallel. The guy sits in the lazy boy, I'm just going to sit back, wait for the hardware guys to make my program run faster. Okay, 18 months go by, well now I'll add all these features and it's fast. The processors are fast enough and it'll handle my features. That's over. You can't do that anymore. If you want to add features to your program that you think is really wonderful so people will buy copies of it, you need to figure out how to parallelize that program because it's not going to get any faster on the newer processors. And in the past, because multiprocessors were supposed to be these expensive things, you had to get linear speed up. So twice as many processors had to run twice as fast. That was a common conventional wisdom. Hey, since there's processors there, you get any speed up at all, that's a success. So right now, this thing has 2 processors in it. I can't buy it with 1 processor. I have no idea what value I'm getting from the second processor on this thing. And that's today. 2 years from now, it's going to have 4 processors. I sure hope there's something I'm getting value out of this today. So this is a recurring theme. What's different is why we're doing it. And this is from this long technical report that we've written that's on a website. So why are they doing it? It's not because of some breakthrough in software or in architecture that makes parallelism work. It's because it's actually a retreat from the harder challenges of building a sequential chip in the power of one. If somebody invented technology where you could get a 10 gigahertz microprocessor, boy, you could sell it today. But they can't do that. So the companies are throwing the Hail Mary and going to parallelism. And we're not just talking about, for the Googles of the world, this may not be this is a great thing. If you work at Google, multicore is a great thing. But we're kind of interested in, suppose you're not at Google and you want to run something faster on your laptop. What are you going to have to do that? So kind of remarkably, as I was telling somebody before, because I was president of ACM, I took a sabbatical so I could do the job, and I had more time. And I wanted to do something researchy, and so I said, here was this impending change. Why don't we get a bunch of people across a bunch of these disciplines to get in a room and talk about these ideas and see what the implications of this all. So those are the areas of expertise. Those are the faculty we got together. And kind of amazingly, as we look back, it took us 2 years. 2 years, because first part of the time, there were some ideas, but the first year was just understanding each other's perspective. It's obvious the right thing to do here. Obviously we use spec, and embassy's no good. Well, embassy, the Ambiguet guys, embassy was the right way to go. So it took us a long time to understand each other's perspective. That was kind of like half the time. And then we wrote a draft of the ideas and got a whole bunch of feedback from, including people in this room, and we revised it again. But it took 2 years. But you get to see the byproduct of this. Is what we came up with 7 questions to try and characterize this. Applications, hardware, the programming model system, software, and then how to evaluate it. And then we ended up thinking about it, we kind of drew it like a bridge where the application tower, the hardware architecture tower, the programming model system software to connect them together and evaluation. And then people thought, that looked kind of like the Golden Gate Bridge. That's kind of the view from Berkeley at the Golden Gate Bridge. It kind of looks like that. It's not quite those colors. I think I don't know why. Blue and gold, that's what I remember. It's blue and gold. But we think that's kind of our logo here. So we think, a lot of ideas can be framed around that. And I'm going to go over the components of the bridge to tell you what we're thinking here. So what are we going to do about parallelism? Classically, computer architecture, the program like SPICE or GCC, the way it was coded, God knows when, that is what you tune to. It's not what it's trying to do, it's the actual code is the artifact, and that's the way spec works. So what do we do about parallel codes? Right? There are some, Stanford did the splash ones. Should we really design architectures for this, programs that were designed for the old Dash architecture way back then? Is that the right thing? That can't be right. And so what we came upon in this conversation with a bunch of people is a claim that computational scientists make. There was a small number of what he called dwarfs, originally 7 dwarfs is what he came up with the name, that would dominate the supercomputing area. And so what we did is look at those dwarfs and try to expand them. I think that's what's on the next slide here. So this is Phil Colella, if you know who he is. Here's what he says. These dwarfs, what we define as a pattern of computation and communication, are well-defined things that we talk about, like fast Fourier transfer and disciplinary algebra. He said, these dwarfs are numerical methods. These are going to be important for at least 10 years in supercomputing. Here's the list. That was his bold claim. So I was very excited about that because it was 7, right? 7 is something you kind of wrap your mind about. So imagine if you're going to do a programming language or an architecture, you could say, well, here's what, it's not the code, these are the things we're trying to do. So if you have a better algorithm for fast Fourier transform or a better architecture for fast Fourier transform, work on that. But let's try and make an architecture that can do all of these things well. If it's 7, that's a number we can handle. The spec benchmarks have 20 programs here. And of course, because it's abstract, you can invent new ways to express it. It can be highly parallel. It won't be the code that you're aiming at. And so when we kind of wrote this up, we got feedback from, well, first of all, we brought people at Berkeley from Embedded, and they said they were very skeptical about this high performance, $0 billion market high performance computing thing. What do they know? Compared to the embedded and 1 billion cell phones, right? So they were very skeptical. But, they tried to keep their minds open, and they started looking at the embassy benchmarks and said, wow, those 7 are pretty common. We have to add a few more to it. But, we ended up maybe at 10. When we did a drafted report, he said, well, embedded and computing and the desktop, those were the top 3 that we did, high performance, kind of general purpose, and embedded. What about these other areas? Well, look at these exciting things in machine learning and games and graphics and database software. How can you possibly think you've got kernels like that? So we looked at those, and that took some more time. So what we ended up with is adding more dwarfs and revising a few, and the next chart is what our current list is. So we've got 13 dwarfs here, and we're making a bold claim. The claim is, boy, if you invent an architecture or a language compiler, make sure it can do all these. And if something that can do all these has a better chance to run the exciting applications of the future well. That if you make let's just do architecture. If the architecture you think you'll figure out to do all these things pretty well, that's a pretty interesting set of stuff and that'll serve you well. Now, what we're not saying is that this is the low-hanging fruit. This is not necessarily the low-hanging parallel fruit. What we're saying is these are going to be important. So there's a thing like MapReduce, which is basically embarrassingly parallel. MapReduce is the way Google deals with tens of thousands or hundreds of thousands of computers and how to make it easy to program. What about finite state machines? Well, finite state machines might well be embarrassingly sequential, right? That might be the opposite of that. But it's not like, well, it's sequential, so finite state machines are going to go away, right? If maybe somebody will come up with a great idea of how to cope with finite state machines to make them more parallel, but maybe not. Maybe that's just a fact of life. When you get to the finite state machine piece of it, it's not going to be parallel. Rather than trying to break our backs trying to make finite state machines parallel, maybe we just have to cope with it rather than innovate around it. So roughly, approximately, this color-coded sheet shows what we first looked at, the high-performance computing, which is the first 7 dwarfs there in red. So red means very important, blue means not important. And then as we added to the embedded, you see we added a few more: combinational logic, graph traversal, dynamic programming. And then as we get across there, machine learning added a bunch of stuff to it. You see when we get over here for the database side, the database community is basically the opposite of the high-performance computing, right? Everything the high-performance computing guys cared about basically is cold, and the other ones are hot. But the fact that there's only 13 things on this list is the type of thing we should be able to wrap our minds around and think about when we're trying to invent to catch this Hail Mary. Okay, so that's the quick arguments for applications. Moving to the next tower, what about the hardware building blocks? And so first of all, what's wrong? And this power wall is what's wrong. Intel actually spent who knows how many tens of millions of dollars on a design that they canceled because of and they canceled it in what basically more or less happened within a couple of months. Tens or hundreds of millions of dollars, cancel it and announce the sea change they're going to parallel computing. IBM has been quoting at very low yields on their cell design. That's kind of an expensive processor when only 10% of them work. And then today, modern companies spend much more. We just think it's normal. Of course, you have verification teams that are much larger than design teams, right? That's kind of an indication that something's out of whack. But that's what's wrong. So here's our claim. Small is beautiful. We think to me, I think of it as going back to 1980s architecture. I thought that was a wonderful time, 1980s architecture. Good old 5-stage pipeline. So modestly staged pipelines, simple things, not 1 million bits for the branch predictor stuff and all that stuff. Because basically all those inventions help sustain the sequential performance model, but they are space inefficient and energy inefficient. The MIPS per watt have been going down with these innovations. When nobody cared about the power, that was the right thing to do because don't touch the programming model. Now they say we can't build those. You're going to have to change the programming model. Kind of surprisingly, parallel is more energy efficient. There's this classic CV squared F, where the F is the frequency, V is the threshold voltage, and that if you lower the frequency, you can lower the voltage as well, but you get the squared effect there. That's why Intel, which is run to a power wall, you'd think if you had 2 processors that would make it worse. They are simplifying the processors, which lowers the C-sum and the voltage and the frequency, and so you can get theoretically twice as much performance for the same power in this kind of model. When you build something out of a lot of simple processors, kind of like the RAID ideas, you can add a few redundant ones and improve the reliability. So Cisco, the famous routing company, one of their key router chips is called the Metro chip. It has 188 simple RISC processors. Actually, they're Tensilica processors, if you know what those are. They throw in 4 spares to improve the yield. So if you don't have the 4 spares, it has to be perfect. All 188 have to work. If you throw in a couple of spares, they can ship it with a few broken ones. Sun has this Niagara processor that's designed for 8 processors, but they also sell it with just 6 of them working. So that effectively improves the yields. It's a lot easier, not surprisingly, it's a lot easier, this verification problem, it's a lot easier to verify something that's simple that you replicate rather than something really complicated we design one. So the verification team being much larger than the design team, this will probably be different for what gets called, as I'll say in the next slide, multicore. Is it going to be like the Metro, 188 or 192 identical processors? Well, as you'll see in this slide, we think not. Probably not.
What the relative size of the design teams were for the design and verification for Niagara? Or
I have no idea. I have no idea. Kunli, are you here? Do you know?
Relative to what?
The design team, verification team? I know that this was an unusual product and that it actually taped out on time. This is not a Sun tradition. I remember you know
Wasn't a Sun team.
You have any idea?
How many people?
Yeah, relative design team versus verification team?
It's about about half and half. Half and half.
Okay. So let's talk about I was going to talk about the heterogeneous processors. Are they going to be homogeneous? All be identical or not? So here's a very simple back of the envelope thing, like you might find in a popular textbook. All right. Suppose to go twice as fast as something, you need 10 times the resources. Power, area, power, whatever. Maybe you'd spend it on going faster with that CVS squared, or you have bigger caches or something. Let's make that assumption. And suppose that the program, this Amdahl's law thing that Gene Amdahl said 40 years ago, let's assume that there's a portion that doesn't get faster with parallelism, say 10%. So maybe it's dealing with the operating system, say, but it's 10%. So let's talk about speed up. For the homogeneity with 100 of the small cores, maybe the right thing to say, it can go almost 10 times faster. If you went with 10 of the fast cores, it goes a little bit faster. What's the best? The best is a mixture where you get the part that's parallel, you got 90 simple processors to get that speed up, and then one processor to run the the sequential stuff. One faster processor sequential. That actually gives a much faster speed up. So I think this, obviously back of the envelope thing, I think is an argument as we head for what people call multi-core designs, where we have scores of processors on a chip. There's an argument because of the Amdahl's law effect that we might want some fast ones or a small number of fast ones that don't use up a lot of area and a lot of small ones. That may be the way things go.
Throw in some FPGA.
FPGA is, it's another one of these promising things. Will we be able to compile from C to programmable devices? I think our take on that is that FPGAs are very inefficient first of all, a lot of people have been working on that for a long time without, huge successes. Secondly, they're pretty expensive in power and in area. So it's theoretically a great idea of kind of reprogrammable hardware, but so far it hasn't been a big success. We'll talk about routing later. I think that's an interesting question of whether routing and FPGA technology are very promising.
Sort of an argument for algorithm-specific hardware to speed up the slow parts of your program, regardless of what the hardware is.
Yeah. So I'll take this. I'll try and do short questions, but I'll try to answer that one. We've talked about this a lot, about how customized things would be. I have colleagues who say absolutely in terms of power efficiency, unquestionably, a custom design is the way to go. I have other colleagues that say the von Neumann architecture is an extraordinarily efficient thing, and if you have a bunch of functions that you want to do, that's very power efficient. Kurt Kreutzer, who's kind of the CAD guy in this, he's been in this argument forever, custom ASIC, people who used to be prejudiced against ASICs. What are you? You're not a real person? You design ASICs? You should be, sizing transistors, and they wouldn't even walk down the hallways with the ASICs on the wall because they were so bad. So he's lived his life. He says he kind of feels like this trend that's going on, possibly because chips are going into commercial devices like cell phones, where the lifetime is short, so the change is increasingly important. He kind of feels there's a shift towards, we're in this seismic shift in the embedded thing towards more programmable things. And with software is valuable. And if we use very power efficient processors, he thinks kind of the advantage of a large number of very efficient processors and the ease of change of software is what kind of that seismic shift that's happening in that industry. But this is a wide open area. Who knows about that? Number of sockets per core, I think we need, our view is we need revolution, not evolution. And what the industry is doing is evolution. We need our architecture needs to be involved, but architecture can't do it by itself. So that's the architecture is back. Multi-core is doubling every generation. That's what all the companies are doing today, kind of is conservatively. And we're arguing is the many core that hundreds is what we're doing is the best. It's, if given that we've gone to parallelism, and that's going to be a hard programming challenge, but we've gone to parallelism, we think the most efficient in MIPS per watt, MIPS per performance, MIPS per dollar and everything is that much higher number of simpler processors. And that's one of our flags in the ground here. And we're making an even more pleasant claim for our friends in industry is this doubling every couple of years is going to work for a while, but we think like instruction level parallelism, it's going to run out of steam. So once you get to 32 or 64, which with the doubling every 2 years, maybe it will happen in the middle of next decade, it's going to stop. So people are going to say, we think the way you would bet would be if, whatever that is, 8 years from now, and I have a 32 processor laptop, and Intel or Apple announces the 64 processor laptop, I'm going to say, why waste my time? There's nothing I care about takes advantage of that. I'm not going to buy a new computer. When it breaks, I'll buy a new computer, but there's got to be no reason for me to buy it. So that this is going to run out of steam. And you won't simply be able to transition. The programming model changes when you're thinking hundreds or thousands. And just like what happened with ILP. There were people who said ILP is not going to run out of steam. There were other people who said differently. Companies, place their bets going forward. And, ILP ran out of steam. That's what we think is going to happen without a lot of innovation.
CMOS?
What?
Is that a revolution in CMOS only?
What?
At the top of your last line.
Revolution.
In CMOS only.
I don't quite understand.
Are you willing to do other device technologies besides CMOS?
I have a colleague, Cheming Hu, and his job in the world is every time people say CMOS is dead, is to extremely convincingly, with working silicon, show that it's at least 15 years out. And and so it's not like, although I will surely be retired in 15 years, the fact that it keeps getting pushed 15 years out through like the 1 micron, no one's going through 1 micron because it's wavelength of light. Obviously, any idiot knows you can't do that, right? So we've gone through a bunch of these things. He thinks if you come up with ideas in nanotubes and stuff, we'll take advantage of those and we can keep pushing it out. So I don't see, it's not, the argument isn't the end of Moore's law and CMOS. That's not what I'm saying. I'm saying I believe they'll probably keep Moore's law going. It's the programming challenges of how to make these things easy to program and using hundreds of processors. That's the opportunity for us. If somebody figures this out in any part of the world, you know, the world, it changed. If somebody does this in Korea, writes a programming language in Korean that makes it easy to program thousands of processors, I'm going to have to learn Korean, right? And this won't necessarily be in the United States. This won't necessarily be a Silicon Valley thing. So the programming model here. How to connect them. So this, boy, we really need a good idea here. How to connect 1,000 processors on a chip. There's people in this room who've been doing this for a long time, but we really need a good idea. The relatively simple things are, well, the dwarfs, if you believe in the dwarfs, if you bet the dwarfs are at the kernel of most programs in the future, well, you can look at the dwarfs to get some insight. And one of the insights from the dwarfs is they're not communicating with everybody all the time. They go in phases where they communicate with subsets. I think I have a slide, one example slide that shows that. And there's not a single best topology. It's not like, oh, fat tree, that'll solve it all. You know, there's no single best topology for all these things. The relatively obvious things, since bandwidth and latency are improved differently technologically, is having a bandwidth-oriented network and a separate latency-oriented network for things like reductions and collectives seems like a good idea. That's not a new idea. That idea's been around for a while. People have had 2 types of networks. So we think, by the way, using good ideas that people can print out, we shouldn't throw that idea away. But ideas like, you know, if really the communication patterns are stable for a while and then change, that maybe a FPGA-like solution or virtual circuit switching, maybe these are good ideas. And, you know, people haven't explored it, but we really need a good idea. How should we do synchronization? Another big question here. Is the transactional memory the savior of the whole thing? Once we do transactional memory, everything's going to work fine. End of story, or you know, some more stuff that we do. Is cache coherency all we need? Basically, what the companies are doing is cache coherency. Multicore, the x86 instruction set, cache coherency, end of story, right? I bet they will, my bet is they will add transactional memory to that. And that's going to be their bet. They're going to bet their companies on that, and without you know, us coming up with a bunch of good ideas. So this is an example for 2 of the dwarfs, just showing in kind of as temperature model, if 256 processors talking to 256 processors, who talks to each other? You know, there's different patterns of communication, but these are relatively stable for a while, who communicates with each other. If we had some, say, a virtual circuit or something reconfigurable that could do this more power efficiently than you know, all-to-all communication, that would be an interesting idea. The programming model. So it's, you know, a lot, you know, kind of computers, you know, part of computer science is very processor-centric, another part is very programming language-centric. When I was a graduate student, we took courses on learning all the programming languages, and there were hundreds or thousands. It was just amazing to me there were people out there inventing programming. I don't know how many, there must have been people who invented hundreds of programming languages or something. There was a Tower of Babel in the book that I used. It was programming language all the time. So kind of, I think that computer science, if we just invent the right programming language, we can solve this thing, right? So I think there's kind of a few flavors of this for parallel programming. There's kind of the performance-oriented or hardware-centric ones, often the variant of C, that tries, you know, people are doing parallel to be efficient, so it's got to be efficient. There's application-centric. People don't want to spend all their time writing parallel programs to solve big problems like MATLAB. And then I think the other argument is basically the problem with parallel programming is the semantics are really screwed up in these languages, which makes it hard to program and hard to get efficiency. If we just had the right semantics, we could solve the problem. So it's kind of striking to us, as kind of outsiders, it's pretty clearly programming is being done by people. And there's a whole bunch of research from the psychologists that our colleagues in human-computer interface tap into when they're trying to design human interfaces. They're not saying, I have an idea how human beings work, ignore those psychologists, what they don't. They think, oh, they know something about this topic. Well, approximately, a lot of programming language literature ignores the psychological research. It's not like to say they can tell us how to necessarily the right way to program, but there's a bunch of things they know about human beings, and you may make an assumption that's actually false about human beings. I think just like the old days of instruction set architecture was amazingly companies who built hundreds of millions of dollars on somebody's hunch what a good instruction set is. That's kind of programming language, it seems. In my experience, what was my problems in programming? I'll capture that, my model of how that was hard, I'll capture that in programming language rather than helping with the, looking at the literature, of which there is a bunch out there to read. So, for example, the argument for transactional memory isn't particularly make programs run faster. It's to help with human errors. It can help, even when programmers can make incorrect assumptions, it's kind of a safety net, and that's kind of an argument for that. So our prod to the programming language community is let's integrate the research of human psychology into trying to figure out how to solve these problems. And the flip side of that is, as I have said for a while, is how do the psychologists resolve these problems? Do they just have big flame wars and send email back and forth until somebody gives up? So is that how they resolve problems about human? No, they actually have this crazy idea. Let's do experiments. Let's do statistically valid experiments to reach conclusions on these things, right? And so that's how they resolve controversies. So it's an example that doesn't resolve a controversy, but this person at the Supercomputing Conference said for novice programmers, let's look at, for simple programs, shared memory versus MPI. And clearly, their results for this novice programmer, small programs, was that shared memory was much better in terms of performance, I think, in bugs and things than message passing. So that's not the end of this story, but it's an example of what to do. Now, the reason we don't do human subject experiments is a lot of work, right? It's a lot of work to do a valid human subject experiment. But people on this campus know how to do this, and the Berkeley campus too. In fact, there's rules. You can't just go out and do a human subject experiment. Before you do that, there's somebody on this campus that'll have to approve it. It happens so often, there's bureaucracy associated, but you never know that from computer science, more or less, except for human-computer interface. How about the system software part of the Golden Gate Bridge? It takes kind of amazingly, operating systems and compilers have grown to be millions of lines of code, and the consequences of that is they're hard to change. So rather than do things via compilers, which is kind of the classic computer science answer, what we've been doing, what we are excited about is what we've called autotuners, is rather than the compiler knows in advance has an abstract model machine, you first run stuff on the program you care about and look at different combinations of things to see what actually works on these computers. And then you produce the C code for that computer, and then the C compiler does the register allocation and stuff like that. So they have factors of 2 to even factors of 10 by virtually searching for answers from a restricted space rather than compiling. And maybe this idea is one autotuner per dwarf. So here's a specific example that Kathy Yellick and her students did. And this is for a finite element block, compressed, sparse row, a sparse matrix approach. That's the data structure. And this is how much you're going to work on it in a block. And this is kind of one element of a row, one column, and this is up to 8 by 8. So what you'd think is, with rational computers, what you'd think would happen as you increase the blocking factor, performance will go up. So as you go all along the diagonal, that's the top. So 8 by 8 would be best. That's not the case. For this particular computer, it was 4 by 2 was much, much faster than the upper column there. How could the compiler writer possibly know that? And I can't imagine how, right? It's a combination of compilers, the compiler optimization, the interactions of caches and TLBs, the number of caches. I think experimentally is the only way you could imagine, but they're getting big multipliers through this so-called autocloner approach. Our other advice is there seems like a couple of obvious things that sometimes get neglected, like if we're going to have a parallel programming model, don't wire in the number of processors. It's got to be independent of that, especially in Grow. And support the stuff that really, there's stuff that works in the past, don't throw that out. So task and thread level parallelism, data level parallelism, bit or gate level parallelism, these work. Don't include that. And then kind of remarkably, let's add a few more data types, right? Most programming languages had the same data types that were in the IBM 360 architecture from 40 years ago. We should have more, right? That doesn't cost very much, and just don't forget to do that. And this is basically, I guess, the Mendel-Rosenblum Memorial slide here is, what are you going to do about operating systems? Well, when Mendel gave a talk at the keynote address at ASPOS, he said, this is what I think is going to happen with operating systems. Operating systems used to be the king of the mountain, the only thing that ran, the only one program that ran it, and you took courses in it. He says, going into the future, because the advances of virtual machines and virtual machine monitors, that he thought what would happen instead, we'd have these thin, simple VMs that will run on laptops, and then you'll just link in the operating system functions you need. So that it kind of, ignoring the parallelism thing, that was kind of his vision of the future. Well, that's perfect for many core designs. Right now at Lawrence Berkeley Lab, they have a large multiprocessor, and their image of the AIX operating system occupies 5 gigabytes of DRAM per processor. 5 gigabytes of DRAM in this big monolithic operating system, right? Wow, that's a pretty expensive way to do operating system functionality. This deconstructed operating system model is a much more exciting vision of the future. How to measure success? It took us a while to come up with this phrase, but kind of every time, once somebody came up with it, I had to go back and read the report and make sure I got it right. So, but this is it. We think measuring success is exactly easy to write programs that execute efficiently on many core computing systems. So easy to write, execute efficiently, hundreds or thousands of cores. That's the goal. I would say computer architects' history have skip the first line there, right? Execute efficiently on many cores, we build hard to program things that have high peak performance. That's our history. But we got to embrace easy to write to do that. And these two goals of maximizing, this kind of struggle between programmer productivity and application performance and energy performance. So what's the challenges here? First, just even figuring out on complicated processors how to get performance on even serial processors that, because you're communicating, you want to minimize remote accesses. You're worried about load balancing now. If all your work is on 1 out of 1,000, that's going to be a problem. And how big are things to share and to move? These are the types of challenges that are going forward. Okay, so in terms of, the company's thrown this Hail Mary, and we're going to head towards maybe many cores, 1,000 per chip. What's wrong? We're not ready, right? We're not ready for that. That's what's not wrong. And the other thing, as I said earlier, the other thing that's wrong is researchers can't build believable chips. Only the companies can build real chips. The third thing that's wrong is software people don't start working until the hardware shows up. Here's my simulator. Please figure all this stuff out. In fact, as long as Mendel, I'm sure I saw Mendel here. I remember this when we were working on this multiprocessor project. We had simulators and stuff, and it took us a long time to build the chips. And when the chips showed up, then the Sprite operating system started working and all this stuff. Now, what happens about 3 months after the hardware arrives, they tell you everything that was wrong with it, okay? So you say, thank you very much, thanks for the feedback, and you go away, work for 4 years, come back and give them another shot. And 3 months later, they tell you what's wrong. So that's where we are. So about a year and a half ago at the Computer Architecture Conference, a bunch of us were not listening to the session. We were in the hallway, and we were talking about this. They've thrown the Hail Mary, they're betting the future. And this is true. All of these things, we're not ready, but it takes forever to iterate on this. What are we going to do? So this is what the people in the hall started talking about this, is how are we going to put this in the hands of researchers, and can we avoid 30 years? And this is what we came up with, is since field programmable gate arrays are getting bigger all the time, they're growing with Moore's law, amazingly, you could fit a lot of simple processors on one field programmable gate array. So the big problem of field programmable gate arrays is when you've got a design that you've got to split across a bunch of them. That's very painful, and only a few companies. Some companies do that. The flip is, with Moore's law, you can put a lot of them inside one, so we believe that's going to be a lot easier to do. So you can do a 1,000 processor system out of a modest number of FPGAs, and they're getting better all the time. So basically, that's just empty hardware. Who's going to do the logic design? And with the hallway idea is the computer architecture community would get together, and we would do the logic design that you put in these relatively inexpensive FPGAs that would look like massively parallel computers. And so 10 of us at 6 institutions, including here, made this pact to do that. And the name is RAMP, for Research Accelerator for Multiprocessors. And what we're trying to do is this vehicle to let us innovate and attract a bunch of people together to do that. So here's a quick, why is this interesting? Why were we excited about it? Why did we all add this to our list of things to do even though we were very busy? Well, we could argue that Some big company should build one of these, but it would cost tens of millions of dollars for a custom design. Or a cluster is a lot cheaper. It's still millions of dollars, but they're pretty hard to manage. So what the architecture community has been doing is everything in software, simulators. And the problem with simulators, if you think thousands of processors, is basically zero performance, right? 1,000 copies of Linux. How long is it going to take that to run a program on your simulator, right? Forever. And the other thing we're worried about as researchers is convincing the Intels of the world that we've got a good idea. And, do you believe, my PC is simulating 1,000 computers, trust me, there's no mistakes in the software to display my results. So that's tough. And so this is basically what the ramp bet is. So it's got a lot of the flexibility of simulators, and it's much faster than the simulator, even though it's much slower than hardware. But from researchers' perspective, that's fast enough. And it also has some similarities to the way you design FPGAs or program FPGAs have similarities to the way you do hardware. It's not perfect, but it's similar enough that the companies we talk to find it convincing that if we could do this in ramp, it's believable. And the big thing is because it runs fast enough, you can run whole operating systems, whole applications, that makes it much more credible. So that's the basic ramp bet. When we got back, amazingly for a hardware project, we realized the hardware already was done. Our colleagues, John Warzik, Bob Broderson at the Berkeley Wireless Research Center, had built a general purpose FPGA board that had 5 FPGAs on it. It wasn't perfect what we wanted, but it was close enough and it was economical enough that we could do that. So we've been working on this for a year and a half. And we just broke it up into a few different pieces. One of them, the transactional memory, or ramp red, was done here by Kozirakis, Christos and Kunli. How about that? And maybe some graduate students helped. Christos made it sound like it was just he and Kunli, but I bet there was some graduate students. And so amazingly, it works. It runs the splash benchmarks and some of these other ones. And as they said in the paper that we co-authored together, this is the first transactional memory computer. Transactional memory is a very hot topic. I don't know how many universities have their own design. They said this runs at hundreds of megahertz. This is the first one. We got the first one done. And I kind of believe it. And the payoff here runs 100 times faster than the simulator. This was just running on one board. So that's the ramp red design. Not surprisingly, there's a ramp blue design that was done at Berkeley, and we just got this up and running, fully running recently. It has 256 cores on 8 of these boards, and it runs the NASC benchmarks in the UPC programming languages using these soft cores here. So these are 2 examples of what you might do with ramp. And the vision of ramp, which gets us excited, is we could really bring everybody together. That here, this can run real software, highly parallel, really inexpensive. Every department could have one. Wow, this could be the next standard platform. If you're interested in parallelism, it's perfect, but on a lot of things it'd be useful. So Christos is working with a person in security, and this is a computer that runs fast enough it can run a whole operating system, and you can connect to the internet and see if people can break into it with your security enhancements. So ignoring parallelism is a really exciting platform. We think that's true for a lot of things. It's hard for us to think of things in computer science research that ramp wouldn't be helpful for. So given all the cautions about parallelism, I feel like it's like Al Gore at the end of his movie. It makes like, oh God, we're all dead. I'm just going to go buy a Corvette because it doesn't matter. We're all going to die. so he said at the end, he said, oh, look, don't give up, right? So that's what this slide is, right? So since it's failed in the past, why won't it fail this time? Well, first of all, it can fail. Those of you from industry, there's no guarantees here. Your bet, and somebody may not catch your Hail Mary, right? But there's some reasons to be optimistic last time. The lazy boy era is over. No one's building faster microprocessors. In the past, we'd build parallel processors and some bastard would build a faster sequential processor and everybody'd say, well, why waste my time with the parallel thing, right? There's no bastards left going to do that anymore. There's no faster clock rates, no faster processors, so there's no alternative. And boy, the hardware and software industries are fully committed to parallelism.
If someone did build a faster single core, you could use it in your same architecture. So.
Well, kind of what the power limit. If you came up, if somebody in this audience has an idea with the 100-watt power limit, how to build a 10 gigahertz, 15 gigahertz processor with reasonable CPI, see me afterwards. There's a market. If it executes the x86 instruction set, there's a market for that. Yeah. So I think I don't know any architects I don't think there's any architects out there who says, I know how to do that. I think all of us think we don't have an idea yet. So yes, there's always been the upside of forever, since the first computer, they built one and they said, if we had a dual processor, we could just replicate the design and get more performance out. That's, from the beginning, it's been the programming challenges there. And what's the funny thing is, if we just didn't build faster processors, people would may have taken parallelism more seriously. That threat is gone. And the companies are fully committed. If you went to Microsoft 2 years ago and said, you guys got to worry about parallelism, there were people at Microsoft who said that, they were ignored. Starting last year, let's talk about parallelism. Let's hire supercomputer people, So Microsoft, of course, Intel is really excited about parallelism now. So now if you got an idea, they definitely want to talk to you.
What about the embedded world where,
The embedded world has made the transition. The embedded world is they don't have any of the legacy problems. They're cared about efficiency per watt, efficiency per dollar. So they're already making this the leading edge of the embedded world is over there. An example was that Cisco chip with 192 processors. I know there's people in this room doing, embedded things with lots of processor designs. Basically, this tensilica design is a half a millimeter squared. So, how much smaller you have to get than that? Moore's law going to keep going. We really can do this, right? If you can do hundreds of processors right now in the Cisco chip, you really, in a few generations, can get to 1,000 processors. It really can happen. And then if we talk about single socket designs inside a chip, you can have really high bandwidth and really low latency in there. When you go off the chip, it's going to be slow. But this is somewhat of a new thing as a reason to be optimistic. In terms, if you think of the memory as off, basically all the processors in the socket are approximately it's the same time to memory. You don't have to worry about that. And that's always been a big deal in the past. Maybe that's reason to be optimistic. And then I think the other kind of really out there reason to be optimistic is the open source software movement. So, when the people who are arguing for RISC, it was this legacy software and how can we move the industry, all this proprietary stuff. How is that going to happen? Wow, this is a new world right here. There's one of the things I'm working on is this RadLab thing, and we're making a bet on Ruby on Rails. And Ruby on Rails is just an amazingly innovative, fast-moving thing. I think the first version 1.0 of Ruby on Rails is maybe a year old or something like that. And boy, it's just up and to the right. Very rapid innovation. So there's this software community that used to be very slow moving. There's this other software community that's very fast moving. It's a meritocracy. You put your ideas out there, you put the source code out there, and people embrace it. So there's a community that's moving very quickly and evolving their software. They're not particularly focused on parallelism, but if we can hook that group in, there's reasons to be optimistic. And then RAMP. Right? We can't build chips at all, RAMP gives us a bunch of us promise, we could do pretty credible 1,000 processors things. We can exchange ideas, Stanford and Berkeley could swap processor architectures and run each other's benchmarks, stuff like that. And we could verify those guys at MIT and see if they're...
Is there a place for microprogramming that's not FPGA?
I don't think so.
Okay.
We'll talk about, those of you who know what microprogramming is will see me later to figure out what microprogramming was. So summarizing and then kind of a research agenda thing. So we're staking our claims in the sand here. Dwarfs is a stand-in for parallelism. Many core is the right way to go. The industry's approach of evolution may well fail. The goal is making it easy to program efficiently, running on many core. Look at human-centric programming models, autotuners and deconstructed operating systems, RAMP. And if you like the movie, read the book. So there's a report that's on the website. We've got a bunch of stuff on the website there. So we actually met to talk about the ideas, and then we were done. And so what do we do with this, right? And so we really believe all this stuff we said. So it seems like the best way I know to attack a really difficult problem is to get universities involved, because we're very economical, and it's a lot easier for startups to happen at universities and stuff like that. So what have people done in the past? More or less, they do a program in an area, like, say, programming languages. Let's do parallel languages. And you get all these experts all over the United States, all these different places, and they get together and they meet once when they talk about programming languages. And then you do the same thing in architecture. And that's kind of the way we've done parallel programming for 50 years. So my argument is that's the wrong way to do that. So it didn't work, so there's something wrong with that. What the problem is getting the discussion across all these interfaces, which we've been trying to do for the last couple of years. Part of it is jargon and stuff like that. So why not do it the other way, vertically integrated? Because what you're trying to do is increase the bandwidth between the people who understand these areas, and having them at the same site is going to make this easier. And there's the opportunity of these universities and others to bring a bunch of experts together, get them in the same room, and talk, and this is a way that we can hopefully innovate and catch this Hail Mary.
Isn't that just an analog of the problem we're trying to solve?
Yes. Right. Parallel programming is something like committee work, right? There's overhead and committee work, but yeah. But at least for me, I think it's innovating across these. I can't imagine, if you've got an idea how to do this within one layer, that's a really great idea. I can't imagine that I don't know how to do that. I think we got a much better chance if we do a bunch of these across these industries. And so I think this is all my last slide. So kind of big picture, what are we going to be able to do with these many core architectures? Can we design architectures to make it easier to program, highly productive programming models? And places like this are ideal to do these multidisciplinary research to be able to do that. And this is my last slide. If you want it, there's places you can read more about RAMP or more about the Berkeley view. And this was done with a lot of colleagues. Okay. I think I deserve a hand of applause. Thank you for that. Thank you for that spontaneous show of emotion. Question?
So you mentioned the memory wall. If I can't feed one beast, how am I going to feed 1,000?
Right. So I think what's happened in computer architecture is a lot of smart people have invented packaging ideas, and kind of the computer architects say, nah, I don't want to use that. Right? I'll just use a bigger die. And because a lot of small dies, you can put them together in a lot of ways. How about a bigger die, right? With smaller things. And so there's been a large number of innovations that people have tried and haven't been embraced. So I think, as Krzysztof says, he says, look, there are ideas like multi-chip modules where you stack the chips together and optics that can get much higher bandwidth. There is technology out there for higher bandwidth. Actually, because we have one processor on the chip, basically, or two, we can't run fast enough we don't need that much bandwidth. We have this kind of, if you remember, I would think of the analogy of a Christmas story where the little kid goes out in the bundles, he can't even put his arm down to be warm, his mom wraps them all up. That's kind of the way we do processors today. We wrap a processor with caches and caches and caches, so there's actually not that much, we don't need that much bandwidth.
It's the latency.
So latency, I went to a workshop, and the title of this workshop that IBM invited people, and I think people here came too, was Infinite Bandwidth, No Latency. So they claim there's a variety, inside of IBM, a variety of packaging technologies that can stack these things right next to each other, so the latency is tremendous, much higher bandwidth and much smaller latency with innovative packaging.
And that's back to PIM, processor and memory.
This is actually separate dies, so there's the separate fab. So there's a mixture of processor dies and DRAM dies. But basically, innovative in there's more ways to do I/O and more innovative ways to package than we've done before. We've just ignored, and that's an argument why there'll be bandwidth there. If not, if we still build it with DIMMs over here on a PC board, then there'll still be the memory wall. But there's reasons to be hopeful there. So that's an area I think. I don't know how to do the communication on the chip, but that particular one, I think there's some reasons to be hopeful on. Question back.
So you said that one problem was verification in design. So would the same thing, I think, would happen with many core, right? Because the memory system will become extremely complex.
No, I mean, well, you could do it that way. I mean, the question is, won't the verification problem be just as difficult with a very complicated memory architecture? Sure, hardware people left to their own might, well, you'd bet on that, right? But that's not the problem. The problem isn't how to design a bunch of hardware with high peak performance and good MIPS per watt. That's not what the problem is. The problem is how to design a system that's easy to program in that. Because even if, say, we came up with this idea that if you work, say, a cell, really, really hard to program, but if you work really long time, you can get some performance out of it. It's not like programming is a solved problem on sequential processors, right? It's not like, oh, we can just build software that works all the time. If we make software engineering tremendously harder to get that performance, this will be another reason we'll fail. because it'll just be too expensive to build the software to take advantage of it. There are hardly any programs that get written. So the problem, we claim the problem is easy to program there. So you have to figure out a way to do memory architecture. Right now, hardware guys, over micro, hardware guys are looking pretty good. If we knew what the answer was, I'm pretty sure we could build it. So, some people are used to being beat up. If Intel doesn't ship it, you can't use it, right? That's kind of the software community's been told this for a couple of decades. All those restrictions are gone. People are worried about the future of their companies are at stake. You have an idea you tell us what it is, and we can build it.
So I wonder, where do we get the 1,000-way parallelism from? And if you're Google, it's client server, that's great. If you have 1,000 clients, that's fine. It seems to me that within one program, the only hope is data level parallelism. I cannot imagine anybody writing one program with 1,000 different stuff.
If we go to, I'll just pick a random thing here. Look at that. So we think a bunch of these have a lot of parallelism in it. A lot of these finite state machines don't. A bunch of these too.
Is it all data level parallelism at this point? If you're not Google,
I think,
or is there something else? I agree they're parallel.
It's always been data level parallel.
I think
They
there's
have
an
parallelism, but you have to get the granularity down to get
Yes.
it.
Well, some of these like combinational is just nobody argues it's not bit level parallelism, right? We often can't express it in our programming languages, but bit level parallelism is not a controversy. Computer science embraced that a long time ago. There was so there's some levels of parallelism that are there, and vector architectures and stream things. They're getting parallelism in some parts by narrow data, right? And there's a bunch of this stuff that narrow data is fine. There's nothing illegal about narrow data there. So I think certainly data level parallelism, it's hard to imagine you've got 100 bytes of data and we got 1,000-way parallelism. I'm sure there's some relationship there. But it was comforting to see this claim of the dwarfs, a lot of them are parallel. So, yeah. I think the other question is, suppose you invent this great new thing and it's embarrassingly sequential. It may not do that well on modern computers. You better start thinking of things that are pretty parallel. If you're inventing new ideas, you better learn about parallelism if you want it to go fast. So maybe that will help us inspire some more things. I'll talk to you. I have another, maybe this will help make Google's software as a service more popular. Many-core may show us towards software as a service, but go ahead.
So you argued against multicore by saying nobody needs two processors in your laptop. You're not sure why you have that. How else, or multicore, how else?
Actually, the exact argument is, I think at 2 or 4, so there won't be arguments. The question is, we think that'll run out.
What applications on your laptop are going to make you want to buy a 1,000-core processor?
Antivirus software. I think what you're saying, what's going to make you buy 1,000 software runs 1,000 processors? Yeah, what are you going to buy, right? This is what I'm saying, right? We need to figure out the answer to this problem. Let me put it this way. If one of us figures out the answer to this problem, so that we're teaching freshmen how to program in some new way and design architectures in a new way that they can easily program 1,000 processor system, that's not a big deal for them. And it's, gets all the benefits of power efficiency and performance and all that. They know how to do that. The world beats a path to your door. There's not a Nobel Prize in computer science yet. They may make one and give it to you. They'll get the first Nobel Prize in computer science if you can solve that. But you're thinking, well, 1,000-way parallelism, that's only high-performance computing. Nobody cares about that stuff. That's not what we're claiming. We're claiming we got to, if we can make this commonplace, but that's not a big deal. Like, here's an example. Who in the world can program a terabyte of data, right? We don't think that's a big problem. Well, what's the problem with that? Make things bigger, right? So we've solved the terabyte of data thing. That's a lot of transistors, right? Can we figure out a way to make 1,000 processors things no much bigger deal than a terabyte data? You could say, well, who would want a terabyte of data in my laptop? I can come up, we can imagine reasons for that, or a terabyte disk and stuff like that. Why would you ever want that? Well, videos and stuff like that. We can use up data. Can we make processors really easy to use? And if we can, this will happen. Suppose we don't. Geez, what the hell are our industrial colleagues going to do in a few years, right? Will people stop buying computers, right? And so I think there's reasons to be skeptical of this, sure. But kind of the purpose of what we were saying is, well, boy, if I
I hope a bunch of places like Stanford and Berkeley start working on this, and I sure hope one of us solves this one. And if we do, this will be revolutionary.
Doesn't that slide you have up there argue against this, Dave? That, and I'm struggling with the granularity. That you talk about the problem of writing parallel programs. It's a generic problem.
Yeah.
Yet you've identified 13 classes of problems with fairly well-defined approaches, algorithms, communications in those 13 dwarfs.
There's been a lot of research on those.
Right, so why wouldn't one conceptualize 13 software macros that are programmable so that the trick is to not to write a parallel program, but to map your problem onto one of these 13, and therefore the programming problem is a lot simpler.
Yeah.
And you may have to write a lot of lines of code on all the other crap, but if you look at where 99% of the cycles are going to go, they're going to go inside these 13 modules, aren't they?
Right. That's a claim. This is not a claim. This is a hypothesis. That's a hypothesis, is that there are a lot of important programs for which what you said is true. That's a hypothesis, right? We haven't proven that. If that's true, then that's promising. So a specific example is MapReduce. MapReduce is the guys down the road invented this. I thought they invented it to deal with their funny architecture, right? They've got all these computers with almost no bandwidth between them. No, that's not what they say. They say, we thought this was going to be a good model to explore lots of data. An easy to understand model is the MapReduce. First you do the map to thousands of things, and then you do the reduction. This is an easy to program, understand thing. I think they're right. I think we'll probably start trying to teach this in some of our freshmen and sophomores, is teach them parallelism via MapReduce because it's easy to understand. If what you said is true, if this is at the core of a lot of important things in the future, plus some miscellaneous stuff that doesn't run so parallel, that would be a promising thing. We're interested in pursuing that. We're kind of like our flagging around. We think this is a good way to go. We want to go look at this. Now, clearly, finite state machines aren't promising, and they are popular. Steve.
So I might have the answer to where the parallelism comes from, but I'm going to put it in the form of a question. And the question is, why?
Aren't I right? No.
Yeah, exactly. Why do we keep chasing thread-level parallelism, which is finite and hard, when there's process-level parallelism, which is abundant? It's almost infinite out there. It's on your laptop, and it's easy. Is it too easy?
But I think that argument is basically, I don't think I need that on my laptop. I'm not ready.
Now we got 28 processes running right now.
They're not parallel.
You mean independent tasks, is what you're saying?
All at the same time.
I suspect, I don't actually know. Maybe I'm getting some benefit from two processors. I haven't done this study. If I had one processor in this Mac, would I ever notice the difference of having two? I'm skeptical. But I think this basic argument is an art. I just was talking with some people the other day. I think there's an argument that this thread, this rush towards many-core will help software as a service. Google doesn't have any problem with many-core design, right? Microsoft has a problem with many-core design. This could help accelerate the world where, I don't think the next, unless you guys don't invite me for a while, but sometime I'll come, and when I put my presentation, it's this thing, right? It's this, and things are connected to it, right? And I carry these things, and a lot of stuff I do, my data and all that, is a service, right? And I think there's an argument that the Hail Mary, one person who catches it is the Googles of the world, and we'll see a lot more service. That's going to be the normal way we compute. There's an argument that way. That's, I can live in that world. I don't know about Intel and Microsoft, but yeah, that's one thing that might happen. Let me try that side of the room. Go right here.
Yeah.
Which one?
Go ahead, you first.
Yeah. I'm getting a terrible case of deja vu here. 20 years ago.
Are you going to say the word transmuter?
I was a member.
British accent, deja vu, transmuter.
Why the only person in the room from Islos?
Right.
I was on the architecture team at the transmuter.
Right.
I've heard this. I was on the MPI committee, so I'm fully aware of the problems. 1992, I did my PhD thesis in the field. 1993, the parallel processing industry died. And so the internet came along.
Yeah. So
somebody like me take away from.
So here's what's different. Here's what's different. I used to have a slide that mentioned the transmuter. The transmuter claimed in 1988 that microprocessors weren't going to get faster anymore. That company says speed of light's the limit.
uniprocessor performance has to end soon. Right? That's what they said in 1988. And this was the startup company that said this. 2003, the president of Intel says, sea change. No one's building faster microprocessors anymore.
They said that in 1989 too.
What?
I've been in meetings with them and they said the same thing.
I guarantee the president of Intel did not say publicly there's been a sea change. That there's going to be no more faster. We're betting our company on parallel computing. I guarantee that didn't happen in 1980. Transmeta said the rest of the industry has to come to terms with the sequential programs that are getting faster. Transmeta, sorry. Transputer, they were wrong, right? And they got killed by the faster sequential microprocessor. Had no one built faster sequential microprocessors then, surely today we'd be much better at parallelism than we are, right? I think, if you believe in parallel universes, there's a parallel universe that what's the big deal, right? We solved that in 1989 because it plateaued there.
There were other problems.
And the other thing is,
and you pointed to a few of them. It's hard.
Yes. Another possibility is we will fail. We're thrown out there. We might not catch it.
And parallelism is not the computational solution. Functional decomposition is much more useful form of parallelism than some of the examples that you've shown there. Some of your dwarfs are things that happen in a program.
Okay, but let me end the question there and see if I can get some others. But yeah, it's possible this won't work again. There's some reasons to be different now. That's why I have the optimism slide, as opposed to let's give up. One more question there, and then I'll probably have to.
So if you look at the industry right now, what they are doing is they are basically taking their strongest sort of processor and replicating it.
Most of the industry is doing that.
Yeah, most of at least Intel, you could say. And but that ensures is that at least all of the existing applications, even if they don't speed up, in a sense, they at least remain as fast as they are. And now if you replace that processor by, let's say, 50 smaller processors, then we of course have the problem that my word processor, which was relying on that super processor.
I agree.
Okay. Now the thing is that...
that's why companies are doing what they're doing.
Right. Now the thing is that I'm not too sure if these dwarfs, if there's a language which is sort of guided by these dwarfs, would that actually be able to make my word processor utilize those at least 50 or maybe 20 of those to at least be competitive with the current processor.
So I really don't care about Word. I really don't care about. I'm kind of excited about the things of the future. Star Trek. The guys who wrote Star Trek were not rocket scientists. They had imagined. There's stuff that they put in 1967 Star Trek episodes that we can't do today. There's there's software that hasn't been written yet that's really wonderful out there that we would like to use, right? The industry problem, what they're going to do in the next couple of years, I don't recommend, actually, there are some researchers who are trying to work on that. That seems like a hard thing to me. I think let's do clean slate. We can save the planet kind of with a clean slate design. If we can solve it with a clean slate with no restrictions, which we may not, right? I think we might be able to reverse engineer from there to do more legacy-oriented things. But our belief is the exciting applications of the future, the dwarfs are going to capture a lot of the computation. That was the comment over here. We may not be right for old legacy codes. That might not be true, but that's kind of who cares, right? But
in a sense, then doesn't it sort of negate the notion that you had at the start that we are not really interested, that we are not only talking about high performance stuff, but we are also talking about
at the two ends, the high performance computing and the embedded community fully embrace parallelism. You don't have to sell them on it. It's the people in the middle who are selling old software that are millions of lines of code that have problems. Well, those guys could go away. There's a bet in the future that there's just that the Googles of the world and the Nokias of the world. That's what the future looks like, and this part disappears for reasons that you just said.
We'll still need Word, even if it's decoded, right?
I guarantee you we will be able to run Word on the 10 years from now, Word will run on this, okay? That won't be the problem. I would like to believe there's a lot more exciting thing to run on this than Word. And on that note, I would like to thank myself for giving my talk.
For information on other Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.